Hello everyone, good morning to all of you. We are back with the week number 8 where we are going to talk about the measurement of a parameter which is very common to all of you, something you have heard from very early school days, which is pressure. Pressure is a term which probably you can relate to several day-to-day common phenomenon or common activities, and of course we are not talking about the mental stress or mental pressure, we are talking about only the thermodynamic quantity, the pressure. But still there are several situations where you have been introduced to this particular term or you have made use the term pressure. Most common example can be the day to day weather report which you keep on hearing on the televisions or on the radios, where along with the local temperature and humidity they also quite often mention about the pressure, or may not be explicitly mentioning about the term pressure, but very commonly you can keep on hearing the terms like low pressure or depression formed in some part of the country or some part of the ocean, thereby leading to the formation of some local disturbances, maybe a cyclone, etc. And we are going to talk about that very parameter in this particular week. Now, last couple of weeks were a bit light, where the total content of the week was a bit lesser, as we discussed about the measurement of stress and strain and also the measurement of force and torque in the previous week. But this one probably having a bit more content, but I hope most of that part will already be known to you. I shall just be trying to emphasize on some of the associated concepts and maybe introducing a few more. So, the first question that we have to answer is what is pressure? Now, what answer is coming to your mind? What is pressure? We all know that pressure is force per unit area, but which area should we be talking about, or which is the direction of force that we are talking about, that of course we have to be very careful of before we can go for the measurement of the pressure. Now, if we go to the molecular level itself, then let us consider a container like this filled with certain gas molecules. Now, as per the property of the molecules, unless they are at the absolute zero temperature, because of their internal energies, they will keep on moving around quite randomly throughout the entire container, thereby colliding with themselves and also colliding with the walls of the container. And as they are colliding with the walls, if we assume even elastic collision also, there will be a change in the momentum of this. During the collision part, there may be a change in the velocity, so that during the collision they will be transferring a part of their momentum to the wall, or it may be possible that there may be a net change in the value of this velocity, that is the magnitude of v1 and v2 may not exactly be same. Quite often the exit velocity actually is lower than the incoming velocity, thereby causing a net reduction in the momentum of the molecule itself, and that amount of momentum will be transferred to the associated wall or to the adjacent wall. Now, the rate of transfer of this particular momentum will definitely lead to some kind of force. So, this particular molecule, as it is striking the wall at this particular position, it is putting some kind of force to this. This way all the molecules are striking the adjacent walls and each of them are putting some kind of force. So, if we combine the cumulative effect of all this force or momentum transfer of all these molecules on a particular wall, then the force that we get, that is what is associated with the pressure, or the force per unit that area is the pressure. Means if we pick up this particular vertical surface, then whatever momentum that has been transferred by all the molecules which are hitting this particular surface will lead to a certain force, and now if we divide that total force by this particular area, then we get the pressure which is acting on this particular surface. This pressure force or the force associated with pressure always has to be normal to the concerned surface, and therefore, depending upon the contour of the surface, the direction of force may keep on changing. Like the examples shown here, particularly interesting can be the aerofoil one. As the surface profile keeps on changing, the direction of the corresponding pressure force also will keep on changing, because at every point the direction of the pressure force has to be normal to the concerned surface. Like if we pick up this particular point, this is the direction of the force, whereas if we pick up this particular portion of the surface, the direction is this particular one. So, depending on the orientation, the direction of the pressure force will also keep on changing, and that is why while evaluating the magnitude of this pressure, we have to be very careful about which area we are talking about. But what about stress then? Because just 1 week back we are talking about the measurement of stress and strain, and you know that stress is also force per unit area. Then what is the difference between pressure and stress? Both are force per unit area, and then whatever way we have measured stress, the same way we can measure pressure, or even more fundamentally, why you need a separate quantity at all? We could have just continued with stress itself instead of introducing any new parameter in the form of pressure. Now, let us say this is one particular surface and a force is acting at this particular point of the surface, or let me draw it in a better way. Say this is a force acting at a particular point on this particular surface, say the magnitude of the force is F. Now, if we divide this particular force, or if we distribute it into two components, one normal to the wall, something like this, let us say, let us call this particular as Fn, and the other tangential to the wall, let us say this is Ft. Then of course, this is a vector addition. So, the total force F is a combination of this tangential component and the normal component. Now, if we take an unit area around this point of application of this force such that this area is A, then Ft by A, the magnitude will lead to, let us say we write it as sigma t, and similarly if n, the normal component of force divided by area, let us write it as sigma n. These two are the two stresses that is acting at this particular point. This one is the tangential stress, this one is the normal stress. Then what about pressure? Actually, none of these two are stresses. What we have written here are force per unit area, and but this particular part is not correct, because stress refers not to these external forces which are acting on the surface, rather stress refers to an internal force which is originated when the body is getting deformed and is trying to resist that deformation. That means, what I am trying to mean that because of the action of this particular force F, there may be some deformation that is happening in the body. Now, because of its own structure, the body is trying to resist this deformation, and therefore, following Newton's third law of motion, it will also produce a force of equal and opposite magnitude, another force F, as an internal mechanism or as a part of the internal mechanism. Now, if we divide these internal resistive forces into two components, what will be the components? The normal one will be Fn itself and tangential will be Ft itself. You can say that the one which is opposing this normal component of the imposed force is this one, whereas the one which is opposing this tangential component of the imposed force is this one, and they have to be equal to their corresponding external counterpart. Now, the force per unit area corresponding to these internal forces are the stresses. So, the magnitude of the tangential stress sigma t and normal stress sigma n, that remains the same, because this Ft and Fn are same, and also we are talking about the same area, but the difference is in form of senses. Here this Ft and Fn are not the component of this imposed force F, rather they are component of this internally generated resistive force F. So, stresses are internal force or part or result of internal force which are trying to resist the deformation of the body, whereas pressure is purely an external one. And if we continue with this particular diagram, then pressure actually is the normal component of the imposed force, that is pressure is the normal component of this imposed force Fn per unit area, that is this particular one magnitude of pressure will be this particular one itself. However, here we are not talking about the internal component, rather we are talking about the external part. So, in magnitude, purely from magnitude wise, this normal component and pressure, their magnitudes will be equal to each other. However, when this normal component sigma n, normal stress I should say, refers to this particular internally normal component of this internal generated force, P refers to the normal component of this externally imposed force. So, though their magnitudes are different, their senses are their magnitudes are the same, their senses are completely different. The stress refers to the internal forces or corresponds to the internal forces, whereas pressure refers to the normal component of this externally imposed force. And another important factor is that pressure or rather the force corresponding to pressure will always point towards inward, that is, it is always compressive in nature, always pointing into the surface. for this. So, if we try to compare force and pressure, then of course, just as I mentioned, pressure refers to the external force, whereas stress is generated because of the internal forces developed within the body to resist any kind of deformation. Pressure is always compressive in nature. That is, if I just clean up this particular mess a bit, then if the force is acting this way, that is into the surface, then pressure will correspond to its normal counterpart. However, if the force is say acting outwards and its normal counterpart is this F n, then this one will not correspond to pressure, rather its opposite. Like if we can draw something like this F n bar, let us say, these are all vectors, I am not putting the arrow. So, pressure will correspond to this F n bar. It is always compressive in nature, always pointing into the surface. That is not related to stress. Stress can be compressive or tensile or maybe shear. Shear actually referring to this tangential part or the like just shown in the diagram. We can have tensional stress where the force are actually pointing outward. We can have compressive stress, and we can also have shear stress where the force is acting parallel to the surface, but pressure is only related to this compressional part. Then pressure forces are always normal to the surface, but as can seen from the diagram, stress can be at any angle. Like we can see here, here we are having a cube and forces acting parallel to each of them. Now, if we break them, here also the surfaces are, in the second case also surfaces are parallel to each other and the forces acting normal to the surface. However, if we look at this particular case, here the force is acting, here again the force is acting normal to the surface, but it is not an orthogonal direction, because here we are talking about the surface which is not parallel to any of the orthogonal axes. So, the pressure force will always be normal to the surface, and magnitude is direction independent, or to be more specific, pressure is a scalar quantity. Of course, force associated with pressure is a vector like any force, but pressure itself is a scalar quantity, because at a particular point the magnitude of pressure remains the same coming from all possible directions, and that is why pressure is a scalar quantity which does not have any direction dependency. However, stress, it is not a vector, it is a its magnitude can be unequal, that is at a different, at the same point stress in different direction can be different, and that is why it is not a vector, it is actually a second order tensor, whereas pressure is a scalar which can also be viewed as a zeroth order tensor. And now pressure can be measured directly, which we are going to learn in this course, but what about stress? We have already learned some basic mechanisms of stress measurement. Stress can't be measured directly because stress is only internal to the system. What we can measure is generally strain, that is deformation of a body per unit initial length scale. And now the deformation or the strain can be related to the stress through Young's modulus and maybe Poisson's ratio to get an indirect measurement of the stress, but there is no way you can get a direct measurement of the stress, which is possible in case of pressure. Pressure we can have a direct measurement, and there are infinite number of devices, there are lots and lots of different kinds of mechanism by virtue of which we can directly measure pressure. Now that direction independency is given by the Pascal's law, which all of you have definitely learned at the school, that is at a particular point on a liquid or maybe on a gas, also on a fluid, if we apply pressure, then force is transmitted equally in all possible direction, which essentially proves that pressure is a scalar quantity, and that also has lots of applications in practice. Like a very simple situations, here you are having a sphere, just consider the sphere to be extremely small, so that the pressure remains uniform throughout the entire body of the sphere, and now there are 4 outlets, each having a different area. Then the force that is acting at this particular surface, if that force is F, then corresponding pressure will be force divided by the area small a. This is the pressure which is acting at point A, or force you are putting at point A. Now at point B, that is this particular point, what will be the force then? Then FB, pressure remaining the same, should be equal to P into the area, where area is twice of A, and so if we put back the expression, it will be twice of Fa. So, it is area is double, accordingly the total force is also double because pressure remains the same. Similarly, at D, here area is 4 times. So, the force which is acting at D is again the pressure into the area of D, that which is 4 of A, and that is it is 4 times of force which is acting at point A, which is this particular one. One possible application, you must have seen the application of hydraulic jacks, where you have two connected cylinders filled with certain fluid, generally liquid. On one of the cylinders which is having a smaller diameter or smaller cross section area, we are putting some kind of force like this, and that gets transmitted through the fluid body into the other cylinder, into the piston on the other cylinder, where the area is much larger. Accordingly, there is a magnification of the force despite pressure remaining the same, and that we can use for doing much heavier work, just like lifting a car. So, at this particular point in this particular cylinder, the pressure which is acting P1 will be equal to F1 divided by A1, where F1 is the force that you have imposed initially, and pressure remaining the same, P1 will be equal to P2. So, the force which is acting on the car or on the second piston will be equal to P2 into the area of the second one, which is A2, and P2 equal to P1, and putting the expression for P1, we have F1 into A2 by A1, or if we write F2 by F1 is equal to A2 by A1. So, if A2 is 10 times of A1, there will be 10 times magnification of the force. So, this comes from the Pascal's law, which you already know, and this there can be several practical applications of this. But now we need to classify pressure into a few categories before we go for the measurement, because we need to be very sure which pressure we are going to talk about. This is the most common kind of definition or classification of pressure. Generally, whenever we are trying to define the value of pressure, we do that with respect to certain reference length scale, and the most common reference can be the atmosphere itself, or I should say the atmospheric pressure. Atmospheric pressure is the most common reference that we generally take. Now, if this is the point where we want to measure the pressure, then we can do in two ways. One, we can define the pressure at this particular point with respect to the atmospheric pressure or with respect to our reference, or we can define it with respect to a reference where pressure, absolute pressure is, or rather I should say the pressure is really 0 or truly 0. Now, when we are doing this with respect to the atmospheric pressure, then we call that gauge pressure. Here the spelling, both this particular spelling and this particular spelling, both are applicable depending upon which language system you are using. I shall be sticking to my definition like this. However, when you are evaluating the magnitude of pressure with respect to absolute 0 pressure, then we call it absolute pressure. So, if PA refers to absolute pressure and PG refers to the gauge pressure of the same location, then what will be the relation? Absolute pressure will be equal to gauge pressure plus the atmospheric pressure, and therefore, once we know the atmospheric pressure value at a particular location, then either gauge pressure or absolute pressure will allow us to calculate the other one. However, if we are talking about a point where the pressure is lower than the atmospheric pressure, then what we should do? There again, like a point here whose absolute pressure is lower than the atmospheric pressure. Of course, we can define the absolute pressure because we are always defining with respect to the absolute 0, and so there will be a positive value of this absolute pressure. However, if we calculate gauge pressure, then gauge pressure will be negative, because here like in the first case, our absolute pressure was greater than gauge pressure, because the actual pressure was greater than atmospheric. So, gauge pressure was positive, or I should say absolute pressure was greater than atmospheric pressure, accordingly gauge pressure was positive. However, when we are doing this particular case, here the absolute pressure is less than atmospheric pressure. So, the gauge pressure is negative. So, we can define it either by a negative gauge pressure, or there is an alternate way of doing this, which is the definition of vacuum pressure. Vacuum pressure refers to, vacuum pressure we use, the term vacuum pressure we use only when we are talking about an absolute pressure lower than atmospheric pressure. In that case, this vacuum pressure is defined as P ATM minus P absolute. It recognizes the fact that the absolute value of pressure is lower than atmospheric pressure, so that we get a positive value of this vacuum pressure. Now, if we compare this with the definition of the gauge pressure, then what we are going to get? If we compare this, then from the first definition, absolute pressure will be Pg plus P atmospheric, and from the second definition it will be equal to P atmospheric minus P vacuum, which is gauge pressure is equal to minus of vacuum pressure. Vacuum pressure will be a positive quantity and gauge pressure will be a negative quantity at this particular location where the absolute pressure is lower than the atmospheric pressure. So, both gauge and absolute pressures are used. You will find pressure measuring devices, pressure transducers or pressure gauges which are coming in both ways, that is some devices which can give you absolute pressure or some devices which can give you the gauge pressure. Quite commonly you can find gauges where it is clearly specified whether it is measuring the gauge pressure or absolute pressure. What is the unit of pressure measurement, can you say? Of course, the most common SI unit is force per unit area, that is Newton per meter square, which is called Pascal. But 1 Pascal being extremely small quantity, quite often we deal with kilopascal, which is 10 to the power 3 Pascal, or megapascal, which is 10 to the power 5 Pascal. But one unit which is very common in practical use for industrial application, that is bar. 1 bar refers to 10 to the power 5 Pascal, that is 100 kilopascal or 0.1 megapascal. Bar is generally a very well used, probably the most well used value of, or I should say the unit of pressure that we commonly use in engineering. Now, these are in SI units, but we can also have British units. Several pressure measuring devices you will find where the measurement is given in terms of British unit. Here the most common unit is PSI. PSI refers to pound per square inch. That is, it refers to a force of 1 pound weight, that is the weight of a body having a mass of 1 pound divided by the area of a 1 inch square, or a square having side of 1 inch. Now, what is the conversion factor between the two? We can easily put the relation between kg and pound and meter and inch, and you will get that 1 bar is equal to 14.0538 psi. So, this is a very common relation. You will quite often find that in some laboratories, maybe at your college or universities, or even when you are going to some industry for your professional purpose, you will find the pressure measuring devices are given with unit of PSIA or PSIG. Do not get confused, their unit actually is PSI, but this A or G refers to, if A is there, then it is giving you the absolute pressure, whereas if G is there, it is giving you the gauge pressure. You have to add the atmospheric pressure to the second case to get the absolute value. Another very common, I should not say it is commonly used, but another possible unit of pressure that is generally used for very low pressure, like when you are talking about a point whose pressure is somewhere very close to the absolute zero, well below the atmospheric pressure. There, if we go for a vacuum pressure or gauge pressure kind of measurement, there may be lots of errors, because because we have to understand that atmospheric pressure itself is not a constant. At sea level, the standard atmospheric pressure 1 atm, atm is also commonly used as a unit for pressure, is given as 1.01325 bar. That is slightly above 1 bar, and that is the reason of having bar as such important unit of pressure. Now, 1 atmospheric pressure is not 1 bar, but slightly greater than this. But this is that pressure value at sea level. This is the normal atmospheric pressure, but at different locations on the planet, the value of pressure can keep on changing. Even at the same location also, the value of pressure may fluctuate depending upon the weather condition, and therefore, when you are talking about such low pressure levels, then small fluctuation in the atmospheric pressure may lead to significant amount of error in the absolute pressure value at this. In that case, we sometimes use another unit which is called 1 torr, TORR. 1 torr is extremely small value. Instead of writing 1 torr, I should write that 1 bar is equal to 750.062 torr. You do not need to remember this particular conversion factor. 1 bar is about 750.062 torr. There is another quite commonly used unit of pressure which is in terms of mercury column, but I shall be coming back to that shortly afterwards. Common units of pressure can be either in terms of bar or kilopascal, or in terms of PSIs, sometimes in terms of atmosphere, and if you are talking about very low pressure, we may also have to deal with this torr. And the one which I shall be talking later on, that generally is given as millimeter of mercury column, which we shall be discussing very shortly, and that can also be related to torr or bar or PSI. Another classification of pressure that is very important in fluid mechanic measurement is the terms static and dynamic pressure. Now, just consider the picture that is shown here. Here we have a channel through which some liquid is flowing. Actually, I should not say liquid, some fluid is flowing. It can be liquid or can be gaseous, but effect is more pronounced in case of liquids, and actually effect can be quite pronounced in case of gases also, when this value v, the velocity is high. Now, if we are measuring pressure at this particular location by using some kind of tapping which is parallel to the flow or which is normal to the flow direction, that is fluid is allowed to flow in its normal course without affecting the fluid velocities, then it will give you a certain pressure value, and this pressure is known as the static pressure. However, if we mount the pressure measuring device this way, then the fluid elements which are flowing in this direction, as they come in contact with the tip of this, then at this particular position, to satisfy the no slip boundary condition, its velocity has to become 0, because it is in contact with the stationary surface now, and so its velocity will become 0. Now, as the velocity is becoming 0, then what is happening? It is losing all the kinetic energies, and as it is losing the kinetic energy, this entire kinetic energy gets converted to pressure. Thereby, the pressure measurement that we get at this particular point, this measurement will be greater than this particular value, because in the second case the kinetic energy also gets converted to pressure, and therefore, this kinetic head gets added to the static pressure to give you a higher value of pressure, which is known as the stagnation pressure. Stagnation refers to the stagnation of the fluid at this particular point, also called the stagnation point. Now, let us clean up the diagram. Let us say this particular point is 1 and this particular point is 2. Here the 2 refers to actually the stagnation point. Now, if we apply Bernoulli's equation at these 2 particular point, or maybe one plane through 1, another plane through this stagnation point. The one, let me be more precise, and this one refers to the point where we are measuring the static pressure. So, let us say here the pressure is P, here the pressure is P naught. Then if we apply Bernoulli's equation, then at point 1 we can write P1 plus half rho V square, rho being the density of the fluid, plus Z1, Z being the elevation of location 1 or this point 1 with respect to certain datum, is equal to P2, which is equal, let me just write P2 now, plus velocity is 0 plus Z2. Now, if Z1 and Z2 are equal to each other, which is frequently the case, we can neglect that. So, P1 becomes P plus half rho V square is equal to P naught at the stagnation point. So, we are seeing that this P naught is higher than the pressure at point number 1. So, this P is the static pressure, P naught is called the stagnation pressure, and this is often called the dynamic pressure, that is the kinetic head or the pressure gained because of the conversion of kinetic energy to pressure energy. This is called the dynamic pressure. In fluid mechanics, we can easily measure both the static pressure and the stagnation pressure. However, dynamic pressure is not that easily we can't evaluate dynamic pressure directly, rather we go for both static and stagnation pressure measurement, and from there we can calculate the dynamic pressure as their difference. In fact, this also provides a very easy way of calculating the velocity of the fluid, because what we can easily see that V square will be equal to 2 by rho into P naught minus P, or V is equal to 2 by rho into P naught minus P. So, if for a flowing stream where the density rho remains constant, if we can get a measurement of the static and stagnation pressure, then using this very simple mathematical formula we can get the value of the velocity of the fluid, which is one of the very important way of fluid velocity measurement using a device called pitot tube. We shall be talking about this later on. Now, let us come to the, once we know this kind of classifications, that is absolute on gauge pressure and also the static and dynamic pressure, let us talk about a few instruments of pressure measurement. And the first one that we have is dead weight pressure tester. It is a very simple mechanism. However, this is generally used more for calibration of the gauges, not for common pressure measurements. That is why they are generally available either in the standard laboratories or places which are used for manufacturing of pressure gauges. Now, here we have a chamber generally filled with certain liquid, certain heavy density fluid, and one side of this chamber is connected to this plunger pump. By controlling this plunger pump, by operating this one, we can change the pressure inside this chamber. Now, on top of this chamber we have a piston and we have standard weights, or rather on top of the piston we have a platform where we can put in some weights. On the other side of the piston we have the gauge which is connected, and this is the gauge which is going to be calibrated using this test facility. Now, initially the chamber is filled with certain fluid and it is initially at some pressure. We can control the pressure of this in two ways, one by operating the plunger pump and also by changing the weight on top of the piston. So, what we do, initially put certain kind of force or standard weights on the piston. So, let us say we want to get a measurement of 10 kg force, that is 10 kg force refers to 10 into 9.81 Newton, that is 98.1 Newton. So, what we shall be doing? We shall be taking standard weight of 10 kg and that will be put on top of the piston. So, the initial pressure may be quite high compared to the initial weight of this, the weight put by this piston may be quite high now for the fluid inside the chamber. So, we start the plunger pump and we keep on operating the plunger pump, thereby increasing the fluid pressure by adding more and more mass of fluid inside the chamber till the moment this piston and weight assembly starts to float. It starts to float means now it has reached some kind of pressure balance, that is the pressure of fluid inside this is sufficient, just sufficient to balance the weight of this standard weight. Then whatever value, whatever reading the gauge is showing, that should be equal to this 98.1 Newton, that is the gauge may be pointing to a location somewhere here. So, we can put the mark of 98.1 Newton. Now, we can change the weight on top of the piston and thereby setting up a new value and accordingly modify this. Like suppose in this next case we have set up force of 60 Newton. So, once the system becomes stable, then wherever the pointer is pointing, that has to be 60 Newton. This way we can keep on calibrating our pressure gauges and also we can recalibrate any existing instrument. This is a very standard assembly and we can by precise control of the plunger pump and the weight and also this gauge calibration procedure, we can get extremely accurate measurement, something in the range of maybe 1 in 1000 ppm, that is in every 1000 parts there may be error of just one part. This level of accuracy we can easily reach with this. However, there are a few concerns that or considerations that we have to be mindful of, like the friction which may be acting between the piston and cylinder. As the piston starts to float or it starts to move because of the increase in the pressure inside the chamber, some energy may be lost because of the friction. There will be viscous stresses, of course, because we are talking about a fluid which is which starts to move inside the chamber because of the action of the plunger pump, and viscous stresses may get developed. Significant viscous stresses may get developed inside the chamber. There can be thermal effects because of the operation of the pump. Energy gets added to the fluid inside the chamber itself, and that may change the density of the fluid and also other associated properties. Buoyancy is another factor. As we are interested to get the piston floating into the fluid, buoyancy is definitely an important factor. Local gravity also may keep on varying. So, where you are doing this experiment, that also matters. Therefore, for every different location and for every scenario, it is important to calibrate the tester itself before we can start calibrating pressure gauges. So, deadweight pressure tester is more for calibration purpose, but similarly balancing the weight of some external thing to get the value of pressure is used in another very common kind of device, where instead of using solid we keep on using fluid, or to be more specific we can keep on using liquid columns, and something which falls under this manometry. You definitely have heard about the term manometers, and that is what we are going to talk about here. In manometers we have a liquid column to balance the force. Just look at this. This is there are generally two broad kinds of manometers. This is the first one, which is called the well type manometer, the other one is a U-tube manometer. In well type manometer we have one big chamber or shell and connected with a small diameter tube. So, both are connected. This is the connection here, so that fluid can keep on moving in and out of the tank and also the cylinder. Let us say the tank is having a diameter of A1, the cross section area of A1, and the cylinder is having a cross section area of A2. This datum is the initial level of fluid in both tank and the cylinder when both are at equal pressure. Now, we have imposed a pressure P1 on the tank and a pressure P2 on the cylinder. Because of that, if P2 is lower than P1, then there will be a reduction in the fluid level on tank 1 or on the big tank, thereby displacing some fluid from the big tank into the cylinder and leading to the formation of a water column, or I should not say water, it is fluid column, generally liquid column. So, if we now write a pressure balance we can write with respect to which point? Let us say this is the level that we pick up to write a pressure balance equation. So, what is the pressure that is acting on the tank side? The pressure will be equal to P1 itself. Similarly, what is the pressure that is acting on the cylinder side? Cylinder side pressure will be P2 plus the pressure corresponding to the weight of this liquid column. Now, how much is the weight of the liquid column? Weight of the liquid column will be let us say rho is the density of this liquid into g is the gravity into volume of this liquid column will be A2 into H plus delta H. This is the volume of the liquid column. This divided by the cross section area of the tube. This is the pressure, or we can write P1 minus P2 is equal to this gamma into H plus delta H, where gamma is rho into G. Quite commonly we use a subscript m to denote this is the density of the fluid inside the manometer or the manometric fluid. Similarly, gamma m is the rho m into G product. Now, this delta H can be related to this area is A1 and A2. How much is the displacement of fluid or change in volume of fluid in tank 1? This is the initial fluid level, this is the final fluid level in tank. There is a difference of height delta H, and we also know the cross section area. So, the change in fluid volume in tank 1 or reduction in fluid volume is just A1 into delta H, and that fluid where it has gone, this is we are talking about a liquid which is incompressible. So, the volume has to be conserved, and if we assume the volume to be conserved, then whatever is the reduction in the volume in tank, that has to be the gain in volume in the cylinder. Now, how much is the change in volume? the cross section area is A2 and there is change of height h. You have to mindful that this was the initial level, this is the final level. So, from there we can say that delta h is equal to A2 upon A1 into h. If we take it back to the previous equation, P1 minus P2 is equal to gamma n into h plus A2 upon A1 into h, or 1 plus 2 upon A1 into gamma m into h. So, by choosing this ratio A2 by A1 at the design level itself and also the density value gamma m, or I should say the density value rho m or the value of gamma m, we can relate even significantly large pressure levels P1 to in terms of h. How we can define a sensitivity of this instrument? Do you remember how we defined sensitivity in the very first week of this? Sensitivity refers to the change in output with respect to the change in input. Now, what is output here? Your output is this change in the liquid column height h, and how much is your input? That is the pressure difference P1 minus P2. So, how much is that? That is equal to 1 by 1 plus 2 by A1 into gamma m. So, this is the sensitivity of the instrument. If this A2 is extremely small compared to A1, that is A2 is negligibly small compared to A1, in that case P1 minus P2 is equal to, or I should say is nearly equal to gamma m into h, that is manometric fluid density into g into h. So, assuming the fluid density to remain constant and gravity can, this g, gravitational acceleration, can also be assumed to be constant, then we are having P1 minus P2 to be a linear function of h, and therefore, on the this particular cylinder surface we can also put proper scale or length scale, which can be directly calibrated in terms of the pressure difference. This. So, this well type manometer is the first kind of manometer, a very simple instrument, but we can get quite accurate measurement if we just by knowing the value of this gamma m and also this ratio of A2 upon A1, which generally is provided by the manufacturer itself. So, well type manometer, however, there is one problem. This kind of things, or actually any manometer, they are not that much suitable for dynamic pressure measurement, as long as we are looking, because they need sufficient some amount of time for this liquid column to get developed and get settled at a particular elevation. And therefore, if we are looking for too frequent change in the value of pressure, we may not be able to capture the corresponding value of h properly. That is why manometers are excellent devices as long as we are looking for static pressure measurement, and also we have to be careful of the range of pressure. They are generally not suitable for very large value of this P1 minus P2, whatever may be the choice for rho m or the ratio A2 by A1. As long as we are working with low to moderate pressure difference levels or pressure levels, and there is more or less static or steady state condition, manometers are very good devices for pressure measurement. However, if you are looking for either measurement of very large pressure or also very small pressure difference between this P1 and P2, or also if we are looking for very frequent changes in pressure, we may have to look for different devices. But now think about the situation where your P1 is equal to the atmospheric pressure and P2 is equal to 0. How can we have P2 equal to 0? Let us just close the top of this cylinder, and the area, that is this area on top of the liquid column, let us evacuate this using some vacuum pump or etc. Then what will be your relation? Going back to this particular equation, your P atmospheric will be equal to 1 plus A2 upon A1 into gamma m into h, or if A2 is extremely small compared to A1, then this just becomes gamma m into h, that is rho m into g into h. So, we can get a measurement of the atmospheric pressure, and that is what we do in case of a barometer, which is just a modification of this well type manometer. Here we have just one liquid pool which is open to atmosphere and a small diameter liquid column cylinder which is generally a capillary tube, and as the atmospheric pressure gets applied on this, if we take a pressure balance at this particular location, then the atmospheric pressure which is acting at this particular point has to be balanced by this particular liquid column. This particular liquid column or weight of this liquid column must balance the atmospheric pressure which is acting on the free surface of the liquid pool. Commonly mercury is the choice as the liquid, and accordingly here if we compare the areas, generally A2 is refers to a capillary tube which is having an extremely small diameter. A2 really is extremely small compared to A1, and we comfortably can equate this one to be equal to rho mg into H being the column of this mercury inside this. Mind you, we can have liquids of any density or any kind of liquid in the column, but one advantage we get is this H is equal to rho m into g, that is H is inversely proportional to the rho to this manometric fluid density. Therefore, if we are using a fluid having low density, something like water is not very low density, but compared to mercury it is extremely small, then this value of H will be much larger. Density of mercury is quite high, 13.6 times more than water under normal atmospheric condition, and therefore corresponding value of H is also 13 to 14 times lesser compared to what we would have got with water itself. Now barometers are very standard devices used everywhere in the world and for ages, and also this simple relation gives us another way of defining a pressure scale, which I have mentioned a few slides back. Now standard atmospheric pressure, as I have mentioned, P ATM is equal to 1.01325 bar, or maybe if we write in terms of pascals. So this into 10 to the power 5 Pascal. Rho m for mercury is 13560 kg per meter cube. Small g can be taken as 9.81 meter per second square. So if we combine this value, your H comes something like 76.17 centimeter. That is, under standard atmospheric condition, the height of this mercury column will be about 76 centimeter, and that provides another scale for pressure where we can easily relate one atmospheric pressure to this height of height of mercury column, or as a matter of fact a column of any liquid. So quite frequently we take, as a normal conversion, we take 1 atmosphere as 76 centimeter or 760 millimeter of mercury, and as I mentioned earlier about torr, 1 torr is actually 1 millimeter of mercury. Therefore, this is equal to 760 torr. So liquid column height can also be a quite frequently used pressure unit, which we can instead of mercury we can use any other fluids also and easily get a conversion. Now well type manometer is one of them, but before I move on to the next one, we have to be careful that in this evacuated portion, perfect evacuation is never possible in practice. So some amount of mercury vapor may remain there. However, under normal atmospheric condition or I should say normal temperatures like 20 to 30 degrees Celsius, which is the normal atmospheric temperature, the vapor pressure of mercury is extremely small, negligibly small. So we can easily carry on with this relation. However, if we are talking about significant value of this vapor pressure, then this relation needs to be modified. In that case, we have to write this one as P ATM minus P the vapor pressure of mercury, or whatever fluid you are using in that so called evacuated portion should be equal to gamma m into G, and this should be the correct relation. So that correction, if we are looking for extremely highly or extremely accurate value of this atmospheric pressure, then this vapor pressure correction must be considered. So the next kind of manometer that we get, the other variation where we do not have a liquid pool, rather we just have one tube which is bent in the form of an U. One side of the tube, or rather both the arms, can be connected to different locations. We can also keep one connected to the location where we want to measure the pressure, other being open to the atmosphere. Accordingly, we get some kind of difference in the fluid column level, and that difference can directly be related in terms of a scale like shown in diagram. The scale can be calibrated like this. Height h can be directly calibrated in terms of any unit of pressure, bar or psi or mercury column, whatever we want, and accordingly we can get a pressure measurement. So, if we take say this is the level along which we want to measure, get a force balance, let us say rho w is the density of the working fluid which is connected to this pressure P1, and rho m is the density of the mercury manometric fluid. M may not be necessarily mercury, it can be any other manometric fluid also, and then on top of this, from this particular elevation to this particular position, let us say this distance is y, and this to this distance is x. We can have some other fluid connected to this portion also. Let us say this fluid is having a density of rho f. Then if we take a pressure or balance or force balance at this cross section BB, then at the left hand side we have P1 plus rho w into h plus y into g is equal to P2 plus rho f g into x plus rho m into h into or g into h, or P1 minus P2 is equal to rho m g h plus rho f g x minus rho w into h plus y into g, or let me be consistent, g into h plus y. And quite often we would like to represent this one as divided by rho m into g, so that we can convert this one to some kind of length scale. Then it just becomes h plus rho f by rho m into x minus rho w by rho m into h plus y. In most of the practical cases, this P2 remains to be the atmospheric pressure and rho f become density of air, and in most situation, particularly if we are going for a mercury kind of fluid, you may have rho m to be significantly larger than both rho f and rho w. In that case, P1 minus P2 upon rho m into g will nearly be equal to just h. So, just the measurement of h itself is going to give you the value of the pressure that you are looking for. However, if the value of rho w or rho f is significant, then we have to consider them during the calculation itself, which is not a very difficult one. Once you know all these density values, you can easily calculate the value of the pressure difference between P1 and P2. Or another important thing is that this one, particularly when this P2 is atmospheric pressure, you can directly get a measurement of the gauge pressure using this manometer, because P1 minus P2 is the one that you are evaluating, which is precisely the idea of gauge pressure. Means what you are getting is P1 minus P atmosphere, that is P1 gauge or P gauge pressure at location 1. So, U-tube manometer can easily be used for calculation of gauge pressure. However, if we are looking for an absolute pressure measurement, then P2 should be equal to 0 if we want absolute pressure measurement. Quite often we use this kind of manometer for differential reading as well. Like think about, we have a flow stream through which some fluid is flowing in one location to other, and we want to get the pressure difference between these two locations. So, this is our location 1, this is our location 2. Then we can easily connect a manometer between these two locations and accordingly get a reading. Like it may be possible that this is the manometric fluid which is showing and elevation difference of h, and on top of the fluid we have this x that is left with. Now, if we across this particular section say BB, if we take a force balance again, rho m is the density of the manometric fluid and rho w is the density of the working fluid. Then on the left hand side you will be having very similar way P1 plus rho w into h plus x into g, and on the right hand side you will be having P2 plus rho w g into x plus rho m g into h. From there you can get P1 minus P2, which is the difference in pressure between location 1 and 2. This kind of manometers are called differential U-tube manometers or just differential pressure manometers. U-tube manometer can have different kinds of variations. If we here also the same way we can calculate an expression for sensitivity, but that will be quite similar to what we got in case of well types. Now, if we are looking for extremely small pressure difference measurement, that is this P1 minus P2, then or if our manometric fluid is having a density lower than the working fluid density, then how we can do it? You can see that the situations that we are talking about here, always the manometric fluid density, that is this rho m, has to be greater than this rho w or rho f. However, if rho m is lesser than this rho w or rho f, then definitely we can't use this, because in that case the working fluid will come down and push this manometric fluid in the upward direction. And in that situation, therefore, what we do is just to invert the manometer in a configuration like this. This is called an inverted U-tube manometer. In case of inverted U-tube manometer, let us say this is your location where you want to measure the pressure. This is your location 1, this is your location 2, and here the manometric fluid is having density lower than the densities of rho 1 and rho 2. If we again take a pressure difference or pressure balance between location 1 and 2, then what we are going to get at point if we take say a pressure balance at this particular location BB, then what will be your pressure on the left hand side? Your pressure will be P1, P1 is the pressure at this particular point, minus there is a column of height H2 of liquid rho 2. So, rho 2 g into H2 minus if there is a column of height H1 minus H2 of manometric fluid. So, rho m into g into H1 minus H2. What about the right hand side? P2 is the pressure at this particular location, minus there is a column of height H1 of liquid density rho 2 g into H1. So, P1 minus P2 will be equal to in the first case it should have been rho 1, sorry this. So, it should be rho 1 g H2 minus rho 2 g H1 plus rho m g H1 minus H2, and we can separate it out into two components. That is, if we take say the H2 part out, then we shall be having rho 1 minus rho m into g into H2 minus rho 2 minus rho m to g into H1, and now depending upon the value of rho 1, rho 2 and rho m, we can easily calculate the pressure difference between these two locations despite the density of the manometric fluid being lower than the density of both the involved fluid. Quite often in inverted U-tube manometers actually use air as the manometric fluid, and if you are using air as the manometric fluid, then this rho m is negligibly small compared to both rho 1 and rho 2 in most of the practical cases. In that case, your P1 minus P2 will be what? It will be just rho 1 g H2 minus rho 2 g H1, and you can go for the subsequent calculation of the density, or I should say the pressure difference in terms of whatever fluid you can go for. like if rho 1 is the fluid that you want to scale the pressure difference, then you can write this as P 1 minus P 2 by rho 1 into G is equal to H 2 minus rho 2 by rho 1 into H 1. So, inverted U-tube manometer is just a variation or inversion of the conventional U-tube manometers, and then we can use very light manometric fluid or at least manometric fluids having density lower than the working fluid density. Now, there are two ways we can increase the sensitivity of these manometers, because we know that the sensitivity in manometers is always given in terms of the change in elevation or elevation of the liquid column divided by the pressure difference. And so, if we want to increase the sensitivity, somehow we have to increase the elevation of the liquid column. One way of doing this is to change the manometric fluid density, but that may not always be most practicable one, and therefore, we can go by just modifying the design itself, we can change the sensitivity of the instrument, or rather increase the sensitivity of the instrument. So, I shall be quickly discussing about two of the methods. One is to use the inclined tube manometer. It is the well type configuration or quite similar to the well type configuration. You can see here, the instead of having a vertical tube, we have inclined the tube to some angle. This angle is B. Now, this is supposed to be the initial datum level. This is the initial datum. In both well and the inclined tube, the fluid was at this particular level. Now, because pressures P 1 and P 2 have been imposed on this, which are different to each other, P 1 greater than P 2, then there is a reduction in the water level or fluid elevation in the well. So, this is the reduction in the elevation level of fluid, which let us say is delta H. Corresponding to this, there is an increase in the elevation of the fluid. So, let us say this is a datum, this is the final position, and so there is a change of H, elevation H between the two. Then how much is the total net difference in this? So, net difference, if we if we take this as our working section, and if we take a pressure balance, then the same way we can write that on the left hand side your pressure is just P 1, on the right hand side your pressure is P 2 plus how much is the height of this? Height of this column is rho m g into height is h plus delta h. However, this h plus delta h, actually in this diagram this h is shown as this, let us call this L, where L refers to the length of this column along the tube or in the inclined way. Now, h plus delta h is the total elevation difference between the fluid level. However, L is the length along the inclined tube from this location up to the tip of this. So, what is their relation? So, we are getting a triangle something like this. If we draw the triangle properly, then this is what we are getting. This one is our L, this one is h plus delta h, and what is the intruder angle? The intruder angle between them, this particular angle is given as B. So, this particular angle, let us say this angle is A, and A is 90 degree minus B. So, what is the relation between them? So, h plus delta h divided by L is equal to sine of A, that is cos of B. So, if I put it back here, so it will be equal to P 2 plus rho m g into L of cos B, and by changing the value of B, therefore, we can keep on changing the value of L or this particular ratio itself. Definitely the value of L will be much larger compared to the value of h plus delta h, and it will be much easier for us to identify the length of the liquid column in the inclined tube. Even for much smaller value of pressure difference between P 1 and P 2, we can easily calculate this. The other way of increasing the sensitivity is the use of micromanometer. In case of micromanometer, we are still using an U-tube manometer, but here both the edges or lengths of the tubes are connected to one large dimension tanks or some kind of bulbs. And here all we are using a second fluid which is also known as the gauge fluid. Now see here carefully, here we have three fluids. We have a manometric fluid rho m, which is this shown by this hatched, is the manometric fluid. Then we have a gauge fluid which is shown by these dots, which is having a density rho g, and now we have the working fluid which is just by the white space. Initially this was the level of the fluid, this was the initial level. This is the initial level of the gauge fluid in both the tanks. On top of that we have the working fluid having density rho w, and this was the initial level of the manometric fluid. Now as soon as we are putting a pressure difference P1 and P2 between the tank, or P1 minus P2, then there is a delta Z amount of reduction in the gauge fluid elevation on the left hand side. Correspondingly both these tanks are actually having same cross section area. So a cross section area of capital A. Now because their areas are same, so there will be the same amount of change in the elevation or increase in the elevation of gauge liquid level in the other thing, other height or other bulb. But because of that, there is a, as the delta Z amount elevation difference is happening in the bulb, there is a much larger change in the height of this gauge liquid column in this, which is given by this y by 2. Correspondingly there is y by 2 amount of increase in the elevation on the other side of the manometric fluid. So now along this cross section PQ, if we take a pressure balance, then what we are going to get? On the left hand side we have first P1, which is the pressure which is acting here. Then we have the working fluid of density rho w. So we have rho w g into how much is the height of this? Height is h plus delta z. So h plus delta z is the height of the working fluid. Then we have the gauge fluid. So how much is the height for the gauge fluid? It is rho g into g into how much is the height? Its height is, if you see, z is the height from the initial between the two initial levels, initial level of the manometric fluid and initial level of the gauge fluid. So let us put z. There is a reduction in this, so there is a minus delta z minus y by 2, oh sorry, there is a plus y by 2. So this much is the total height. See, from this point to this point it is z minus this small delta z, and now this is your y by 2. So rho g into z into this particular elevation is on the left hand side. Now what about the right hand side? On the right hand side we have P2 plus a column of the working fluid rho w g into how much is the height of the working fluid? There is an increase in the height of the gauge fluid by of amount delta z. So that much reduction has taken place on the working fluid side. So that is h minus delta z. Then we have the column for this gauge fluid. It is rho g into g into how much is the height for this gauge fluid? It is z plus delta z minus y by 2, plus we have the manometric fluid rho m into g into how much is the manometric fluid? It is just y. Now as all the fluids are incompressible in nature, so there is a delta z amount of reduction in the gauge fluid height in the bulb. So change in volume is capital A into delta z, capital A being this area, and then corresponding increase of elevation in the other arm on the left hand side. How much is that? Small is the cross section area into y. This much is the change that has taken place, or I should not say y, actually this is the initial level. So y by 2 is the change that has taken place. So delta z is small a by capital A into y by 2. We can take it back here. So P1 minus P2 is equal to rho wg into h minus delta z minus h minus delta z. So that corresponds to rho w plus the gauge fluid this is on the left hand side, and we are taking from the on the right hand side we had this is coming plus rho mgy. So delta z goes off, that is rho wg into for this was I should not have struck this out, h minus delta z minus h minus delta z, actually h goes off. So 2 delta z remains, and this 2 delta z can be converted in terms of areas as small a by capital A into y, plus for the gauge fluid rho g into z. So here z goes off, but 2 delta z is there, which again becomes small a by capital A into y minus y plus rho mg into y. And if we now take this g into y as common, which is generally done, what we have? We have rho m on one side plus how much coming from rho g. So small a by capital A being smaller, we can write this as 1 minus small a by capital A into rho g plus, or it is also negative, so small a by capital A into rho w. So we have the expression for this pressure, and when this small a by capital A tends to 0, then we have P1 minus P2 is equal to rho mg y. Okay, sorry, this nearly equals to rho m minus rho g into g into y. When this area of the cross section area of this capillary is extremely small compared to that of the bulb. And now if the difference between the manometric fluid density and gauge fluid density is smaller, then y will also keep on increasing in proportion. Therefore, by suitable choice or suitably combining this manometric liquid and gauge liquid, we can get much higher sensitivity using this micromanometer, and therefore we can easily use this for very small delta p measurement as well. So this is the way we can increase the sensitivity of manometer, and overall there are several types of manometers that we have discussed. In the next lecture we shall be solving a few numerical examples to see the application of these concepts in practical fluid pressure measurement. But so far I would like to complete today's work here. If we just take a quick recap, we have started with the difference between pressure and stress. Then we talked about the concepts of static and dynamic pressures, absolute and gauge pressures. Then we first talked about the dead weight tester, which is generally used for calibration of pressure gauges. Then we talked about manometers, generally two broad level of classification, well type and U tube manometers. And we have also discussed about the barometers as a variation of the well type one, and the inverted tube manometers, which is actually an inversion of the U tube manometers. And then we discussed about the sensitivity enhancement of manometers, two different mechanisms. One that is inclined tube manometer, which is generally more relevant to well types, and other is the micromanometer, which is more relevant to the U tube ones. So just go through these lessons before we start the next lecture, and therefore I would like to sign off from here for today. Thank you very much till the next lecture.